Alright, this is geometry, and we're talking about biconditionals and definitions. Okay, so the main thing you need to be able to do is understand what a biconditional is. Okay, now biconditional is actually a really unique property, and you've actually worked with it before. And it actually works like this. P, if and only if, and it looks like this, Q. Okay, and this is an if and only if, and it's actually an if you want to go straight up math logic or math statements. It's an if with two F's. Okay, and it means if and only if. And so it's kind of like one of those finalized statements. But what it actually means is both conditional and converse are true. So if I went forwards and backwards in this statement, so if I went from left to right, it's a true statement. If I went from right to left, it's a true statement. So that's what happens when a biconditional definition is happening. Okay, so let me see. Let's get an if-then statement in there. So if the sum of the measures of two angles is 180, then the two angles are supplementary. So that's a conditional. Now, if I reverse that and make it conditional, or I'm sorry, make the converse of that statement, if two angles are supplementary, then the sum of the measure of the angles is 180 degrees, and that's true, I can make a biconditional and say two angles that add up to 180 degrees are supplementary. No, sorry. Two angles are supplementary if and only if their angles add up to 180 degrees. Okay, so that's one way of just saying this you know, this type of stuff. Okay. All right. Now, when you are working on this section, just be very careful to just think about what you're saying. Think about it in a conditional sense. If you want to say it in a conditional sense, you want to have an if logical statement. So if your hypothesis is what you're saying, and then you want to have then conclusion. Okay, so you want to have that being said out. All right, if you have that being said and worked on, then everything else is going to come with it. So you can actually take a plain old statement and make it into two, a conditional and a converse. So like, for example, if array is an angle bisector if and only if it divides an angle into two congruent angles. So the first statement is array is an angle bisector. Okay. The second statement is if it divides an angle into two congruent angles. So you would use it in conditional. So if an angle is a bisector, then it divides an angle into two, or an angle bisector is a bisector. I'm sorry, if array is an angle bisector, then it is dividing an angle into two equal spots, or equal angle measurements. Then you would say the converse, and you would just switch the hypothesis and the conclusion, and you would say if an angle, or if array divides an angle into two congruent angles, then it is an angle bisector. So you can say it that way and mix up a biconditional with an actual conditional. So now you got to remember a couple of things. A good definition uses clearly understood terms. These terms should be commonly understood or already defined. And a good definition is precise. Good definitions avoid words such as larger, sort of, and almost. Okay, a good definition is reversible. That means you can write a good definition as a true biconditional. So those are some good ideas of what a definition is going to be given. Okay, now that doesn't mean you still can't come up with counterexamples, because sometimes you can write something and it looks true, but then you come up with a counterexample and all of a sudden it becomes false. Okay, so you have to be very careful to think around all logical avenues when working with this. Okay? Alright, and I think that, yep, that's pretty much it, just covering everything. Alright, so guys, that's it for biconditionals and definitions. I will talk to you later, and see you on Friday. Bye.